Okay, today I'm going to be demonstrating getting up and running with VisualGDB and the STM32 Blue Pill. So you can use the STM32 Blue Pill in Visual Studio. And this is going to be a full walkthrough starting from a fresh install of Windows here. So the easiest way to we're going to search for VisualGDB here on Google, and we're going to go to download, and it's going to tell us to install Visual Studio Community Edition. So we're going to go over here, right-click the link here. We're going to go down here, and we're going to download Visual Studio. You need the latest version of Windows update installed and everything. So here we are. And what you need to have installed, you need to have the Python environment installed and desktop development with C++. And we're going to go ahead and install this. While this is downloading, we're going to go ahead and download some additional tools. We're going to go ahead and download the VisualGDB installer right here. And let me see, purchase. And VisualGDB is not free. It's a 30-day trial, 30-day limited trial. And the version that you want to buy, you can buy the embedded version. It's inexpensive and it's worth purchasing for $99 US or 79 euros. I recommend getting the custom version. It costs a little bit more, but it allows for side-by-side installation of different ARM frameworks, which is very useful for when you have multiple different versions. When you've got different projects and you develop them against different versions of the framework or the supported libraries or whatever. Once again, the software isn't free, but it is worth it, and you'll see why here in just a bit. So we're going to continue with some of our downloads. We're going to need STM32 CubeMX. Okay, next we're going to install, we've got a couple things to install. We've got STM32 CubeMX and VisualGDB. Go ahead and install this. Next, accept, next. I'm gonna leave the Android edition off. Now we're going to install STM32 CubeMX, which requires Java. Okay, so there's not much to this. You have the blue pill and the little programmer dongle here. You care about the 3.3 volt, the ground, the clock, and the I/O lines, which are the 4 lines here. It's fairly straightforward. The pinouts on these, I've noticed some of them are in different orders, so you just need to be sure that you've got them connected in the correct order. And that's all that's needed for wiring this one up. I went ahead and I put a jumper between pins A9 and A10 for one of these demos. It's right there. Okay, so next I'm going to demonstrate a simple project not using STM32 Cube, just using Visual Studio. So we're going to start. We're going to launch Visual Studio. we're going to say create a new project. We want to use the embedded project wizard. Going to say next. Just leave that, and I'll put the solution in the same directory. Okay, start trial. And VisualGDB has some useful tutorials on their website. So we're going to create an embedded project. Just say next. Driver selection. We want the ARM GCC toolchain. Install. Okay, now we're going to find the STM32 F103C8, and okay, you want to allow side-by-side installation, which is one of the features from the custom version. Download the STM devices. Okay, looks like we have the devices installed. We're going to leave the implementation here as minimal for the semi-hosting stuff. I'll show you why here in just a minute. Go ahead and say next. And we're going to do use the LED blink example from the hardware abstraction layer. The LED on the Blue Pill is GPIOC pin 13. And we're going to have a half-second delay. Say next. Debug using OpenOCD. More downloads and installation. Debugger programmer, ST-Link v2. And one important thing under advanced settings. If you have one of these Blue Pill devices, frequently they're pre-installed with some sort of Arduino firmware, so we're going to want to say STM32F1X unlock 0. That will allow the chip to be unlocked and erased if it is locked. So we're going to finish here. One other utility we probably need to pick up is the ST-Link utility. And kind of mix this in here. We'll do the ST-Link utility here, and I'll just show you can connect to the device, see the memory contents. You can set the option bytes, like if you want to disable or enable readout protection, so on and so forth. To disconnect here, click over here. Here's our code. Our source file is embeddedproject1.cpp, and you see we have the GPIO write pin and the hardware delay. Going to start and run this. Here we go. Now we have the LED blinking. And so here's what you can do with the debugger. A lot of you people have experience only with Arduino and stuff. You can set these breakpoints here, and it stops the code. So if we wanted to watch a register, let's say GPIOC, we can either go to Quick Watch, and here's our registers here is our output data register. So we have 1 on output ODR13. If I set a, and what we can do here is we can add a watch to it, full on watch. I'll show up down here in the watches window. And watch this. So here we have ODR13. Run again. Here it's changed to 0, 1, 0, 1, and 0. And you can see the LED toggling with this. So that's it for the initial basic demo. Next, I'm going to demonstrate STM32 CubeMX for building a new project. And keep in mind, STM32 CubeMX is a bit of a memory hog and seems to have some memory leaks that will slow your machine down if you leave it running in the background. Part number STM32 F103C8. Here it is. We're going to go over here, system core for sys. We're going to say debug, serial wire, clock, crystal, high speed and low speed, because the Blue Pill should have both on there. And connectivity, we're just going to do UART1 asynchronous mode, and you see it's activated the IO pins over here. And we're going to do one more thing here with the UART. We're going to enable the global interrupt under NVIC settings. And next we go to clock configuration, use the external clock, and we're going to say we want it at 72 megahertz, hit enter, and it solves the problem for running the clock at 72 megahertz, and we're going to generate code. So now we're going to say project name, oops, and we want the toolchain to be GPDSC. Next we go back to Visual Studio. We're going to say create a new project. Embedded Project Wizard. This time we're going to import the project file. CubeMX project. Go select the GPDSC file that we just created. I'll put the project in the imported project directory. That's for source control reasons. And next, device selection, it's already selected. Minimal semi-hosting, I'll get to that in a bit. Debug method, ST-Link v2, OpenOCD, advanced settings. We're going to once again add that C STM32F1X, unlock 0. And now finish. Okay, we have our source files over here. This is going to be a C file for the for our main program. You notice we have all these comments here. These begin, and what happens is if you want to go in back to STM32 CubeMX and modify your product or your code, what's in between the user code begin and end tags doesn't get touched, and it parses and replaces the things outside of there. Oh, and we also have, it says we have another directory required by the current file. So we say add to project properties. You click add selected directories, and we're going to go over here and we're going to add the solution to source control. And it says it's got projects located outside the solution folder. I think part of that, I might be wrong on that, but I think we'll be good. Let's try this. Okay, so we're going to go here, and now we're going to go down here to the project. Okay, so we're going to go over here, and now we're going to, and I'm going to intentionally put this outside of the begin end blocks here. So I'm going to say char rx buffer 100. That'll be our receive buffer for this UART demo. And I'm going to do this outside of here as well. Okay, outside of the while block. I'm going to say HAL, that's for the hardware abstraction layer. UART receive. We're going to use the interrupt. We enabled that, even though we're not going to mess with the interrupt handler in this first demo. And HUART1. This is just, we're just casting here so we don't get a warning. And this is going to be the RX buffer, size of RX buffer, and I'm going to do -1. And the reason for that is if for whatever reason you're using that buffer and you're placing it into a string or you're writing something, this can protect us against a buffer overrun with null terminated strings. Because this buffer is declared outside of the main routine, it's going to automatically be initialized to 0. And next we're going to call HAL UART transmit and HUART1 date T star TX buffer gonna time out of a second here, and I'll just say and so the reason I'm declaring this as an array as opposed to a char star is so that the size of gives us the length of the array. So next I'm going to start and run this, and I'm going to set breakpoints and see what happens here. So the receive buffer is empty. I'm going to right click here and I'm going to add a watch so it shows up down here. Next step. And the reason we're using this IT method for the interrupt, even though we're not messing with the interrupt handler, is so that it doesn't block for sending the transmission. So otherwise, if we did the standard receive and we were trying to transmit and receive to the same chip here, it would be blocked while awaiting for to receive the data. So we just use the buffer and the interrupt so that we make a non-blocking call for receive. So let's run this. Okay, so now let's look at the receive buffer. Still empty, still all zeros. And now we have hello world inside of this receive buffer. We can go down here and see it in the watch window. So next step, standard loop here, and we're going to send 3 times. Let's see what happens. So we have it 3 times, and it automatically null terminates that string. So if we notice, the size of the buffer that was sent was 1 additional, and it went ahead and null terminated that for us. So that's that. Next, we're going to go back here to STM32CubeMX. Let's say we forgot to enable, let's say, pin C13. I know it's difficult to see. There we go. We're going to make this GPIO output. And we're going to go over here to GPIO. Here, I'm just going to call this user label LED. We'll just leave it as push-pull. Now, before I do this, I'm going to go back over here, and I'm going to commit my changes. Right, so we're going to go back here to STM32CubeMX, and we're going to say generate code. Return back to our project here, and now our code's gone. So we're going to go back here, and we're going to say compare with unmodified. So now we've got this. You could see the changes here. And now we were able to recover our lost code. So now that we've done that transmit and receive, let's make this LED blink. And the LED on the STM32 Blue Pill is connected to the high side, so you're going to want to pull the GPIO pin low on that port to turn the LED on. And the easiest way to toggle the LED is to write to the GPIO output data register. That's not the best way to do it, and I'll explain that in just a second. So we're going to go here, and we're going to say GPIO C ODR, which is the output data register, equals, and we'll just say 0 for now. It's a 16-bit register, and then we'll say how delay 500 millisecond delay, GPIO C ODR equals, we're going to use the rotate left operator, 1 rotate left 13, and that should be our GPIO C13, and then delay another 500 milliseconds, and I will set a breakpoint here. We're going to run. Go down to the watch window. I'm going to add GPIO C ODR for a watch, and we will watch pin 13. So we're going to step over here, go back to our watch window. See, it's still 0, and here it's set to 1. And now it's 0. The reason writing directly to the output data register is not the best way to assign GPIO values is that you might have other things running in your microcontroller. You might have interrupt routines. In order to correctly assign this value, you would need to read in from the input data register IDR the current value or maintain that state somewhere else. And if you only wanted to assign one pin or another, there's a better register for that, and you have the BSRR and the BRR register. And what those do is you write those are 32-bit registers. the ports are 16-bit ports, and so on the BSRR register, you have the leftmost 16 bits clear anything that's a 1 in the leftmost 16 bits, clears those pins, and anything that's a 1 in the rightmost 16 bits sets those. So in this case, we would wish to clear pin 13. So we'll do 13 plus 16 here. That would clear the bit, and then we will go down here and we will set bit 13 only. And to demo that, I'm going to go up here and say GPIOC ODR equals 0x, I don't know, AA. So we'll, or AAAA. So we'll just have a bunch of alternating ones and zeros here. Well, that's interesting. Let's try this again. Here we go. 1 0 1 0 1 0, so on and so forth. Step over. 13 is a 1. Only pin 13 was cleared. Here we go, our 1 0 1 0. Step over, go back to our watches here. 13 was cleared. Now 13 is set, and we don't have to worry about the existing state of any of those pins just to set a single value or clear a single value. So I prefer using that BSRR register. And the final thing I'm going to do is we're going to go back to this this interrupt, and we're going to use a real interrupt handler on this. And so part of what STM32CubeMX builds is this interrupt file right here. And so what you can do is you can go down and you can find your excuse the dog in the background. You can find your interrupt handler here. Here's our UART interrupt handler. There are a lot of different ways to find the interrupt handlers you would want to use. This is just one of them, and this helps to show some of the code navigation features of Visual Studio as well. So you can right-click this interrupt handler that the high-level one calls. You could put your logic in here, but there are some things that you need to do to clear the interrupt, and some of the stuff the hardware abstraction layer takes care of is that, and you can copy that code if you need to tighten up your interrupt handlers and that kind of thing, if timing is even more critical. So you can right click and say go to definition, and then here we have our handler definition here. This is in the code that ST provides for us, and you can see there are different ones. There's a UART receive IT. Let's see. Error flags is reset. So if some errors occur, you just sit down here and you just kind of read through it. And looks like what we want is this interrupt handler right here. You can find go to definition here. And then UART receive complete callback. And we can go back. You can go to the definition here. And then here is the interrupt handler definition. And it is in this how UART file. Now we can go back here to our main file if we wanted to work with that interrupt handler. And we can paste this here, just copy it, and this replaces that other implementation. So here it has this note here. You don't modify it. When you need that callback, you can put it in the user file, which is what we're doing here. So now I'm going to, I don't know. Let's turn on the LED when the receipt is complete. So we'll set a breakpoint here. We'll delete this, and instead of running this code 3 times, we're going to put it here in our main while loop. And let's run this code. So we've got it, we already have this set up to receive. So we're going to run this. And so now let's look at the receive buffer. And here we have it. It sent that hello world this many times, and notice that the last byte is still a 0 because we set the size to the receive buffer -1. And so one final thing I'd like to demonstrate is if you did want to do some debug writing, that kind of thing, we can go up here to, let's say you wanted to print to the command line. So we're going to go up here to the VisualGDB project properties, and I'm going to go here to embedded frameworks, and we're going to go to the fast semi-hosting and embedded profiler. We're going to add this, and that's the reason we don't want to enable the full semi-hosting when we created the project. So we have this added, and now in this receive, let's see. Include standard I/O. Now we have our printf function. I'll set a breakpoint here. If for some reason you don't see the code starting and hitting a breakpoint, you might have a hard fault handler. I'm not sure what's causing it here. Might be something with the debugger. There is a way to get more information with this. I think it's probably just something with the USB hosting on this virtual machine. I've not seen this before. So here it seemed to work fine there. So here we have our 0, 1, 2, 3, and if you remember that that serial data was, what was that, 15 bytes long, so it should be 6 or 7 iterations before we hit the breakpoint. And here we went through 7 iterations before the receive buffer filled up, and then we got our interrupt here. And that's that. Have fun.